This episode of The Controversy describes a scientific experiment. Due to the controversial nature of the event in question, we've elected to keep the identity of the experiment's author a secret. This line makes a border, dividing the area inside from the area outside. The law of the conservation of energy says energy cannot be created or destroyed. Energy can only leave the area, join the area, or transform from one form of energy to another. Let's try to visualize the conservation of energy. Here is an object. The object has weight. We're going to name the object Big Boy. We're going to convert our muscle energy into Big Boy's potential energy when we lift him up. Big Boy will convert his potential energy into kinetic energy when we let go and he falls back down. Let's do that again. Muscle energy raises Big Boy up, giving him the potential to fall. Scientists call this form of energy potential energy. Just like batteries store electrical energy, raised objects store kinetic energy. And just like batteries must be connected to a circuit before electricity can flow, raised objects must be dropped before they can pick up speed. The law of the conservation of energy says the amount of potential energy Big Boy will lose when he falls is equal to the amount of kinetic energy he will gain by falling. Let's change things up a little in order to make this explanation a little more obvious. Suppose we tied a string to Big Boy, looped the string up over a pulley, and tied the end to a fan called Windy. Big Boy is now part of a system. He has the same amount of potential energy as before, only now he is forced to split his potential energy between picking up speed himself and helping the fan to force the air to pick up speed too. Big Boy cannot pick up as much speed as before because less of his own potential energy is available to him. The phenomenon is simple and visible. Big Boy cannot fall as quickly whenever a third party steals potential energy from Big Boy. In these three examples, Slide, Springy, and Blunt gobble up some of Big Boy's potential energy, and the act of doing so slows Big Boy down. On September 11, 2001, 4 hijacked passenger airliners took part in a coordinated attack on the United States of America. 3 of the 4 planes struck their targets, striking the Pentagon and each of the World Trade Center towers. At 8:46, American Airlines Flight 11 struck the North Tower, striking floors 94 to 98. This episode will focus on that single strike in order to keep the explanation as tender as it can be. The North Tower, a redundant structure comprised of steel and steel-reinforced concrete, would continue to burn for another 102 minutes. At that point, the building collapsed, pulverizing itself, reducing 500,000 tons of building to dust and gravel. It is important to this episode to note that it took less than 10.5 seconds for the North Tower to fall. Suppose we separate the North Tower, separating the floors above the area of attack from the floors below. For simplicity's sake, we'll call the floors above Jill and the floors below Jack. We are going to make 3 copies of Jill, setting Jack aside for now. On the left-hand side, we'll ask Jill to free fall through a vacuum, falling the same height that she once stood. An object falling from that height takes 9.2 seconds to reach the ground. On the right-hand side of the screen, let's connect Jill to the biggest meat grinder the world has ever seen, and place Jack inside. When Jill on the right falls, she will use some of her potential energy to grind Jack to dust and gravel. Although Jill on the left and Jill on the right start with the same potential energy, the energy necessary to grind Jack to gravel and dust is so large that Jill on the right is going to take longer to fall. How much longer, you ask? Well, on September 11th, it took Jill less than 10.5 seconds to grind Jack to gravel. Suppose we remove the meat grinder, replacing it with a vacuum so that Jill on the right can fall unhindered like Jill on the left is doing. She would also take 9.2 seconds to fall. Return the grinder, and Jill on the right returns to taking less than 10.5 seconds. Adding and removing the steel and concrete adds and removes 1.3 seconds of additional delay. The collapse of the building added 1.3 seconds to the time it would take for an object to fall the same height through a vacuum. The unnamed scientist who designed the experiment we are repeating must have looked at Jill on the left and Jill on the right and said, "The difference between them is too small, but how would one go around proving it?" The unnamed scientist had an idea. Jill on the left will still fall in a vacuum, and Jill on the right will still pulverize Jack to gravel, while Jill in the middle sinks the same height through water. Jill in the middle is useful. Let's use a metaphor to explain what we mean. Here are 3 shallow zinc tubs. The tub on the left is empty. It will mimic a vacuum on the cheap. The tub on the right is filled with sand. It will mimic the strength of steel and steel reinforced concrete. The tub in the middle is filled with water. Imagine pushing the flat of your hand through the medium in each tub. Pushing your hand through the air is pretty easy. Let's pretend it takes 9.2 seconds to complete the task. The tub filled with sand is the hardest of the 3 tasks to complete. Let's pretend the sand takes 10.5 seconds. When we say that Jill in the middle helps, we are saying that falling in a vacuum is easiest, grinding concrete and steel to dust is hardest, and it stands to reason that Jill in the middle should take between 9.2 seconds and 10.5 seconds to sink. We are going to check whether this is the case in this episode. To begin with, let's cover the idea of terminal velocity. Terminal velocity is the highest speed a falling object attains when falling through a fluid like air or water. When the skydiver jumps out the plane, their speed rapidly increases. When their speed increases, so does the drag they experience. A skydiver's drag will increase until the force of drag slowing them down is equal to their weight speeding them up. From this point on, the skydiver cannot slow down, or their weight gains the upper hand and they speed up. Likewise, the skydiver cannot speed up, or the increase in drag would slow them back down. This balance of forces occurs at a velocity known as terminal velocity. Jill in the middle is a classic case of an object falling through a fluid. The terminal velocity for Jill in the middle is 66 kilometers per hour or 41 miles per hour. Please pause the video here if you are concerned that there might be errors in the math. Armed with the terminal velocity for Jill in the middle, we are in a position to do a temporary calculation, a placeholder calculation if you would. For the sake of clarity, let's rotate the animation of Jill in the middle on its side. She will still sink like she was doing, only rotated by 90 degrees. On the ground beneath, we'll mark a 417-meter long stretch of road. Let's have a car drive at a constant speed of 66 kilometers per hour or 41 miles per hour across that stretch. It takes the car 22 seconds to cover the distance. You'll notice that Jill in the middle could not cover the full 417 meters in that time. Unlike the car, Jill in the middle does not move at a constant speed. She accelerates from standstill up to her terminal velocity of 66 kilometers per hour. From this, we can conclude that Jill in the middle has to take longer than 22 seconds to sink. Jill on the right grinds Jack to gravel. It takes her 10.5 seconds to finish. Suppose we replace Jack with a vacuum, so that Jill on the right can fall unhindered like Jill on the left is doing. She would take 9.2 seconds to fall, like Jill on the left has done. Now suppose we force her to pulverize Jack again. She will return to taking 10.5 seconds. Adding and removing Jack adds and removes 1.3 seconds worth of hindrance. Jill in the middle sinks in water. We've learned that it would take her longer than 22 seconds to finish. Suppose we replace the water with a vacuum so that she can fall unhindered like Jill on the left is doing. She would take 9.2 seconds to fall. Add the water back and she returns to taking more than 22 seconds to sink. Adding and removing the water adds and removes more than 12.8 seconds of hindrance. Therein lies the problem. The official pancake narrative is based on the belief that Jill can pulverize steel-reinforced concrete 10 times more handily than she can sink. We've all waded through water. We've all climbed concrete stairs. Steel and steel-reinforced concrete can support enormous loads, whereas water cannot support a single stone. There is a discrepancy between the event we all witnessed and what we have come to expect from steel and concrete. The law of the conservation of energy has seen discrepancies like this before. They stem from large amounts of hidden energy which we have yet to account for. These large amounts of energy are able to explain discrepancies away. For example, a jet motor is a cartoonish explanation of one way that an additional amount of energy could help Jill to pulverize steel and concrete faster than she is able to sink. Of course, there were no jet engines pushing the tower down that fateful day. The missing energy is going to be found elsewhere. Currently, the best working explanation for the discrepancy is found in the numerous eyewitness accounts describing explosives being used on the day. Explosives would explain how Jack and Jill fell down as quickly as they did. Although these accounts were ignored, the eyewitnesses include survivors, first responders, and journalists.
At 10:30, I tried to leave the building, but as soon as I got outside, I heard a second explosion and another rumble and more smoke and more dust. I ran inside the buildings, the chandelier shook, and again, black smoke filled the air. Within another 5 minutes, we were covered again with more silt and more dust. And then a fire marshal came in and said we had to leave because if there was a third explosion, this building might not last.
Like, it sounded like gunfire, you know, bang, 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 and then all of a sudden, 3 big explosions.
To me, it sounded like an explosion. Then the building, the rolling sound sounded like the building collapsed.
Well, me and Mr. Hesh, Corporation Counsel, were on the 23rd floor. I told him we got to get out of here. We started walking down the stairs. We made it to the 8th floor. Big explosion. Blew us back into the 8th floor.
I was down in the basement. All of a sudden, we heard a loud bang, and the elevator doors blew open. Some guy was burnt up, so I dragged him out. His skin was all hanging off.
This episode used terminal velocity in order to draw attention to the enormous discrepancy in the official narrative. The unnamed scientist did the math, and she understood. Although it's possible to hijack an airliner, and entirely plausible to crash an airliner into a building, it's scientifically impossible to do so in a manner which breaks the law of the conservation of energy. Unfortunately for the innocent peoples of Iraq, Afghanistan, Libya, Syria, and Yemen, her wisdom fell on deaf ears more than a decade ago. This episode used terminal velocity in order to point out the discrepancy. Sadly, terminal velocity could not reveal anything more than the phrase, Jill would take longer than 22 seconds to sink. The unnamed scientist used computational fluid dynamics to do the maths. The animation playing in the background is an example of computational fluid dynamics, and it is the more accurate. This episode invites scientists, engineers, and hobbyists to finish what the unnamed scientist started. Episode 2A ends here, and episode 2B is gated by that invitation. The next episode will need a minimum of 5 YouTubers to use their computational fluid dynamics software to calculate how long it would take Joel to sink. 5 honest experiments would put everybody in a position to throw out the highest and lowest results and average the middle 3. Gating the next episode was not an idle choice. If America's military-industrial complex has come unglued, the world would be better off learning whether the discrepancy of 9/11 is enormous and true. Please, thank you, and good luck. This episode of The Controversy is a little unusual because social media has come down hard on science and history channels of late. NATO is unlikely to be a fan of the science in this episode, and so we've decided to change things up a little. As a result, interested parties may freely dub this episode into other languages and publish their dub on their own channels on 2 conditions. 1. The dub keeps the content and the tone of this video intact, and 2. The dub does not remove this appendix.